So Google actually just dropped something insane and we have to talk about it. So Google dropped something that they're calling quantum echoes. And this might just be the moment the quantum computers actually become useful for real stuff. So here's what happened. Google's quantum team just ran an algorithm on their Willow chip that's 13,000 times faster than the world's fastest supercomputers. And that's not even the crazy part. This is the first time in history any quantum computer has done something verifiable that beats supercomputers. And what does verifiable actually mean? Well, it means that you can run this on any quantum computer of the same quality and get the same answer every time. You can even check it against nature itself. Before this, quantum computers were basically doing party tricks that we couldn't really verify. The big picture. Let's zoom out for a second. The entire story of human discovery has been about understanding nature at every scale. From plants down to living cells down to the molecules that power those cells. But here's the problem. Nature's complexity has always been ahead of our current tools. That's literally why quantum computers were invented in the first place. They were designed to break through that barrier and give us the power to answer profound questions about how nature actually works. But until now, quantum computers have been stuck in the doing science phase. Scientists studying quantum computers today that changed. Now quantum computers are actually being used to study other things to do science on nature itself. What they actually did. Okay, so the algorithm is called quantum echoes. Think about how bats use echolocation to map out caves, or how submarines use sonar to detect stuff underwater. Google basically did the quantum version of that. They took an qubit array on the Willow chip and ran a series of operations forward. These are quantum gates, basically the operations that manipulate qubits. They then poked at one qubit like a butterfly effect, a tiny disturbance in the system. And they then ran the exact same operations backward and reverse. The forward-reverse signals interfere with each other and create this echo pattern. The echo reveals hidden information about how the quantum system works. It's measuring something called an out-of-time order correlator, which is basically how different parts of quantum systems interact over time and space. The technical term is OC, out-of-time order correlator. It's a value that measures sensitive interactions between different parts of a quantum system, not just over time but over space too. It's looking at how information spreads through a quantum system. Why has nobody done this before? The reason nobody's pulled this off before is because these signals are incredibly faint and drowned out by noise. It's like trying to hear a whisper in a stadium during a rock concert. Historically, measuring OTOC in large quantum systems has always been a massive challenge. The signals you're looking for are buried under layers of quantum noise and errors. You need hardware that's accurate enough to extract meaningful data from all of that chaos. But Willow is just that good. Its incredibly accurate quantum gates can run thousands of operations while keeping errors under control. They're using superconducted integration circuits that offer precision that other quantum computers can't match. Plus, they've got clever mitigation techniques. They're not just brute forcing through noise. They're strategically reducing it so the important signals stand out. And get this, they can do milliseconds of measurements in under 1 minute. And the speed is critical because you need massive amounts of data to confirm your results and filter out the noise. Over the whole project, they did 1 trillion measurements total. 1 trillion. And that's massive. And that's a massive chunk of all measurements ever done on all quantum computers combined. This is legitimately one of the most complex quantum experiments in history. The hardware breakthrough. Let's talk about what makes Willow so special. Because this experiment would have been absolutely impossible without it. Willow isn't just fast, it's accurate. Last year in 2024, Google announced that Willow solved a problem that had been challenging scientists for nearly 30 years. And they figured out how to dramatically suppress errors as you scale up quantum computers. Usually with quantum computers, the more qubits you add, the more errors you get. It's been a fundamental problem holding back the entire field. But Willow broke through that barrier. The chip is built from superconducting integrated circuits, and these give incredibly accurate quantum gates. And a quantum gate is like a logic gate in a regular computer. But the qubits, the accuracy of these gates determine how complex of a calculation you can run before errors overwhelm your results. And with Willow, they can run very complex calculations involving thousands of those gates. And that's what allows them to distill the important signals from all the background noise. Think about it like this. If you're trying to hear someone talking in a noisy room, you need good ears. But if you're trying to hear a specific whisper among thousands of conversations, you need superhuman hearing, which is exactly what Willow provides. The real-world application. So here's where it gets practical. You know, NMR spectroscopy, nuclear magnetic resonance? It's the same tech behind MRI machines. Scientists use it to figure out the shape and structure of molecules. Well, why does that matter? Because the shape of a molecule determines everything about how it works. Whether it's proteins in your body, molecules that store energies in batteries, the structure of new materials, whatever. If we want to design better drugs, better conductors, and better materials, we need to accurately understand molecular shape in complex environments. The problem is that NMR has limitations. It's incredibly powerful, but there are things that it can't see and distances that it can't measure effectively. Google partnered with UC Berkeley and used quantum echoes to predict the structure of two different molecules. One had 15 atoms, the other had 28 atoms. And they then verified their predictions using an actual NMR spectrometer in the lab. The quantum computer's predictions matched perfectly, not approximately, perfectly. And the results on the quantum computer matched the traditional NMR. But here is the special part. Quantum echoes also revealed information that isn't usually available from NMR. It can measure longer distances than current methods. It's accessing data that traditional techniques can't reach. And this is huge, because it means quantum computers aren't just replacing existing tools. They are extending them, showing us things we couldn't see before. Why molecular structures matter so much. And let me explain why molecular structure stuff is such a big deal. It's because it touches everything. In drug discovery, you need to know exactly how potential medicine will bind to its target. Like if you're designing a drug to fight cancer, you need to know the exact shape of the cancer cell proteins, so you can design a molecule that fits into it perfectly like a key in a lock. Right now, that process is incredibly expensive and time-consuming. You basically have to synthesize a bunch of potential drugs, test them, see what works, iterate. It's trial and error on a massive scale. And if quantum computers can accurately predict molecular structure and interactions, you could simulate all of that before ever synthesizing a single molecule. You could design the drug on the quantum computer, verify it'll work, and then make only the candidates you'll know will succeed. That could save years of development and billions of dollars. In material science, it's the same thing. Want to design a better battery? You need to understand exactly how the molecules in the battery components interact. Want better solar panels? It's the same thing. Better superconductors? You need to understand the quantum interactions at the molecular level. The shape and dynamics of molecules are foundational to chemistry, biology, and material science. Better tools for understanding molecular structure means faster progress in biotechnology, solar energy, nuclear fusion, and all of it. Now, what makes this one different from previous claims? This is another "a quantum computer did something fast" story. Let me explain why this is fundamentally different from previous quantum computing announcements. Back in 2019, Google demonstrated quantum supremacy. They showed that a quantum computer could solve a specific problem that would take the fastest classical computer thousands of years. That was impressive, but the problem they solved was kind of artificial. It was designed specifically to be hard for classical computers and easy for quantum computers. It didn't have an obvious real-world application. It was like saying we built a car that can go 300 mph, but you can only drive it in a perfectly straight line on a special track. It's impressive, but it's not useful yet, and this is different. This is verifiable quantum advantage with a clear path to real-world applications. And this means three things. 1. It's faster than classical computers at something genuinely useful. 2. The results can be verified and repeated. You can run this on any quantum computer and get the same answer. You can check it against physical experiments. And 3. It directly enables real-world applications that we care about. Before this, quantum computers were solving problems we specifically created for quantum computers. Random circuit sampling, stuff like that. It was quantum computers proving they could do quantum compute things. But this is different. This is probing nature itself, understanding molecules, magnets, potentially even black holes. This is quantum computers being used as scientific instruments to study the world around us. The verification problem. Let me dig deeper into why verifiable quantum advantage is such a massive deal. The problem with previous quantum computing achievements was verification. How do you know the quantum computer actually did what it claimed to do? And if a quantum computer solves a problem that would take a classical computer 10,000 years, how do you check if the answer is right? You can't run the classical computation to verify it. That would take 10,000 years. It's like if someone told you they calculated the trillionth digit of pi in their head. Even if they give you an answer, how would you justify it without doing the calculation yourself? With quantum echoes, you can verify the answer in multiple ways. You can run it on another quantum computer and you can see if you get the same result. You can compare it to physical experiments like they did with the NMR spectroscopy, and you can check like they did with the NMR spectroscopy. You can even check certain properties of a quantum system against what we know from quantum theory. This repeatability is crucial. It's what separates a science experiment from a one-off demonstration. It's what makes this scalable. Think about it. If every quantum computation has to be verified by some external method, that's a bottleneck. But if quantum computers can verify each other's work, that work can be cross-checked against physical reality. And now you're building a foundation for trust in quantum computing results. And that's what makes this verifiable quantum advantage instead of just quantum advantage. This verifiable part is just as important as the advantage part. The telescope moment. The way Google's described this is actually perfect. When we invented telescopes, we suddenly could see planets, stars, and galaxies that were always there, but were invisible to us. And when we invented microscopes, we could see cells and bacteria that were always there, but were just too small to see. This is the same kind of moment, but for quantum systems. Quantum echoes is like a molecular microscope, or maybe accurately a quantum scope. It's a tool that lets us see and measure things that were always there but inaccessible to us via previous technology. The quantum interactions inside molecules, the way information spreads through quantum systems, the correlations between distant parts of a material. These things exist in nature. They're happening right now inside your body, in the materials around you, everywhere. But we couldn't measure them accurately before, and now we can. And just like how the telescope and microscope led to revolutions in astronomy and biology, a quantum scope could revolutionize chemistry, material science, and a fundamental understanding of quantum mechanics. The path from here. So what's next? Well, Google is working on what they call Milestone 3 on their quantum hardware roadmap. A long-lived logical qubit. Let me explain what that means. Well, right now Willow uses physical qubits. Each qubit is an actual piece of hardware. But physical qubits are noisy and error-prone. A logical qubit is different. It's a qubit encoded across multiple physical qubits with error correction. If one physical qubit has an error, the error correction catches it and fixes it. The logical qubit stays intact. The goal is to have logical qubits that can maintain their quantum state for long enough to run really complex algorithms, hours, days, potentially longer. Once you have long-lived logical qubits, you can build a full-scale error-corrected quantum computer. That's the endgame. That's when quantum computers become general-purpose tools and we can, throw any problem at them. But here's the exciting thing about quantum echoes. It's not waiting for that future. It's actually a useful application running on noisy intermediate-scale quantum hardware right now today. It shows that even before we have the perfect error correction, even before we have millions of logical qubits, quantum computers can do useful things that classical computers can't. Now, why 5 years? Well, Google is saying that they expect real-world applications within 5 years. That might sound optimistic, but it's based on this breakthrough, and it's pretty reasonable. They've already demonstrated the core algorithm works. They've already verified it against real NMR experiments. They've already shown it runs 13,000 times faster than classical computers. What's left is scaling it up and refining it for specific applications. And that's engineering work, not fundamental research. It's hard engineering work, but it's a known path. Compare that to where quantum computing was 5 years ago. In 2019, they were just demonstrating quantum supremacy on an artificial problem. Now they're running verifiable algorithms on real scientific problems and matching experimental results. The progress has been exponential. Willow solved the 30-year-old correction problems, and quantum echoes demonstrated the first verifiable quantum advantage. Each breakthrough builds on the last and accelerates progress even further. Within 5 years, we could see quantum-enhanced drug discovery platforms, quantum simulations of materials for battery design, quantum models of chemical reactions for catalyst development,